Welcome to this lecture, Introduction to Experimental Design. We'll be talking about simple experiments, right, where you have two groups and one independent variable. And then we'll also be talking about expanding the simple experiment to a multi-group experiment, but where you still have just one independent variable. Starting off, why conduct an experiment in the first place, as opposed to conducting some sort of descriptive or correlational study? Well, typically it's because you're interested, your goal is to identify cause and effect relationships. Well, why are cause and effect relationships so important, so interesting? Well, one thing, identifying cause and effect relationships allows us to sometimes explain why groups differ or to understand why they differ. Right? So if we see these two groups of people, both groups have been exposed to a traumatic event, maybe even the same traumatic event, but some of them develop PTSD and some don't. Often we want to know why. Why are they different? We want to understand that. We want to be able to explain it. And if you look at correlation research, you can often identify, okay, they differ in terms of having PTSD or not, and they also differ in terms of some other variable, some other life events, some personality characteristic, whatever it may be. But because you're doing a correlational study, it always could be, well, yeah, but that could be something else. It could be another variable that also happens to covary. Or it could be the direction of relationship. Well, does having PTSD make you report that you are this way? Right? So allowing us, doing an experiment allows us to look at, okay, here's this variable we believe explains the difference that causes these groups to differ. Now let's see if it can. And it won't necessarily explain, oh yeah, well this is definitely why, but if you can establish, okay, well, when this happens, it can create this difference, then that's a much stronger explanation for why groups differ than just some sort of association. Okay. Additionally, we can examine whether or not we can change or control behavior. Right? So once we have identified a potential causal agent, so well, if we think doing this causes you to develop PTSD, okay, well then let's do this other thing to prevent it, and we'll see if we can prevent it. So people exposed to trauma, half of them we offer this intervention to immediately after the trauma, the other half we don't. Okay, now we've been able to change behavior, we've changed the outcome, right? We've prevented PTSD, and we've shown it experimentally. Again, establishing, well, because the only way these two groups differed was what we did, doing this thing must account for the difference between the groups, and therefore it caused the difference. Right? Okay, so what are the key components of an experiment? There's three main things. One, the manipulation of an independent variable. You've got to do something differently to at least two groups. In a simple experiment, you just have two groups. You do something differently to one than you do to the other, and then you measure your dependent variable. And if there's a difference in the dependent variable, you ought to be able to conclude that that difference is explained by what you did, your independent variable. And one thing to be thinking about when designing an experiment and picking an independent variable, deciding how you're going to come up with an operational definition of your independent variable is, well, do I need to do a manipulation check? Right? I think whenever I do this to this group and this to that group, that ultimately is manipulating this variable. I'm doing something differently, but are you doing it differently enough for it to have an effect and for it to be observable to the group? So maybe you want to say, look at the study where I think, exposing people to a frightening sound will cause them to sit closer to the person next to them. Whereas people that don't hear frightening sound won't move over to sit closer to somebody else. Okay, that's fine. When picking your frightening sound, you want to make sure that it's loud enough and that it causes fear or anxiety, right? So you might do a manipulation check before you run your study. You get a small people together and you play different sounds for them. You say, okay, could you hear that? Was it loud enough? How afraid did you feel? And then you pick your variable, your independent variable, based on the one that most clearly is actually representing that you are manipulating that variable. You are playing a scary sound that's, again, loud enough and scary enough to be representative of the construct of a scary sound. Right? The other thing to think about is the generalizability of your independent variable. right? So if I'm thinking, okay, I want to see if this scary sound is going to cause people to move more closely together, and really what I'm going for is when people are presented with frightening stimuli, do they seek proximity, or do they want to be on their own because they don't know what's coming, right? If that's ultimately what I'm testing, then I got to think about, okay, the kind of scary sound that I pick, how representative is it of all the scary stimuli out there in the world, right? In a simple experiment, you have to just pick one you think is most representative. As we'll get to a little bit further down the line, going beyond the simple experiment is often helpful because, well, scary sound, but I'm really interested in stimuli in general, so maybe I'll also do a scary picture, or I don't know if there's a scary smell, but a scary smell, right? But if in a simple experiment you're limited to one, okay, pick the one that's going to be most like kind of the scary stimuli that people are likely to encounter in the real world. Okay? And if you don't, you just have to be able to note that in your discussion. Okay, so this scary sound did have an effect. However, this sound may be different from other sounds because it's louder, it's more intense, has more sudden onset, whatever, than typical scary sounds, and therefore, in the real world, you might not see the same effect. Right? So you want to think about those things. Another thing to think about are potential ethical concerns, because when you're manipulating an independent variable, you're typically doing stuff to people, stuff that normally wouldn't happen to them. So you've got to think about, are there potential risks associated with being exposed to this independent variable, and is there potential for harm, right? And so often when we think about harm, we think about immediate harm. Are they going to be hurt right now? And then with risk, we think about, okay, is what I do to them now going to cause harm in the future? Is it going to develop kind of this risk factor? And so you don't want to do anything that's going to cause too much risk or too much harm, but you can cause some harm, right? You can incur some risk, depending on how important your question is, right? And also depending on what you're going to do to address the potential harm and risk. So if you're going to be causing people anxiety, maybe you're going to say, I'm going to do that, but I'm going to have some therapists on standby to debrief people and talk with them if they're feeling anxious. Or everybody's going to be made anxious, and then afterward, after I've measured my dependent variable, I'm going to put them all through a progressive muscle relaxation or some sort of guided imagery to calm them back down. Right? So you have to think about the harm, possibly account for it, and you can cause some, just not too much. And of course, there has to be informed consent about the potential for harm, which is another thing to think about. If I'm telling people that I'm going to harm them, if I'm going to scare them, does that affect how that variable works, right? If I tell you, okay, I'm going to play a loud sound, it's going to be real scary, okay, I'm priming your fear network, so the effect of my scary stimulus might be different than it would have been if I hadn't told you. So can you not inform them of that? You can be vague about it, potentially, right? So, you could say this experiment you may experience uncomfortable emotions, right? Which isn't telling them you're going to scare them. But then you have to debrief them at the end, and the degree to which you deceive them has to be justified by kind of the knowledge that you're potentially going to get out of it. So manipulation IV is one of the big components. Second one, experimental control. Right? And experimental control is about exerting your influence, your control, such that doing everything in your power, such that the difference between groups, your experimental group and your control group, the only difference between those two groups and what they experience is your independent variable. Everything else they experience the same. Well, what should be the same? Primarily, we're talking about setting and time, right? So if you're going to be exposing people to something in one setting, the people that aren't exposed to that thing should be in a similar setting. That way people won't say, well, you found this difference, but it could be because of where they were, because of where you collected the data. Or the other thing, so setting is one, the other one is timing, right? So if I'm exposing somebody to a fearful stimulus, maybe the other group, I'm not doing nothing, I'm doing not a scary sound. But if the scary sound is twice as long as the not scary sound, okay, then more things differ between the groups than scary, not scary. Well, it's scary, not scary, and twice as long versus half as long. Right? So my results would then be ambiguous. Well, did people seek more proximity because they heard a sound for longer, or because it was scarier? right? So you want them to be as similar as possible in terms of setting, in terms of timing, how long they're exposed to things, what time of day things happen, how much time is required of them, the order of events in terms of when the dependent variable is measured. As similar as you can make those things, the greater experimental control you have, and the greater experimental control you have, the better your internal validity. And when doing studies on humans, you can't have perfect experimental control. You can come pretty close with animals because we can manipulate their environments with impunity. With people, not so much. Not a horrible thing. It's just the degree to which you give up experimental control, you're going to be losing some internal validity. Not all, but some. Third thing, so manipulation IV, experimental control. Third thing is power to assign to groups. So the experimenter must be able to and must take responsibility for assigning people to which group or which level of the independent variable they go in. And you do that with the ultimate goal of establishing equivalent groups, right? Because if we want to do something with two groups and then say, okay, now we measure them and they're different, and they're only different because of what I did, well, you have to have some reason to believe that the groups weren't different before you did the thing, before you manipulated the variable, that there was no difference between groups, that they were equivalent. And typically we do that with random assignment, right? Where we randomly assign people to experimental group or the control. In random assignment, you do that to get equivalent groups because, again, as we talked a while back, you're interested in the effect of your independent variable on a dependent variable. There are other variables just in the world, individual differences in people, that will affect how they respond on your dependent variable. Right? When we call those things nuisance variables, because you're not studying them, so they're a nuisance to you. So again, if in my study with playing a scary sound, seeing that people, if they're going to seek proximity or not, people who are already more anxious might be different than those who are less anxious, right? And so if I ended up with a whole lot of anxious people in one group and some pretty kind of chill people in the other group, input my IV, whichever group is the experimental, whichever is control, my results are going to be ambiguous because those groups are different on how anxious they are. Right? And so we use random assignment with the hope that that won't happen. That if you have 50 people in your sample, and let's say 10 of them are really pretty anxious, using random assignment should result in about 5 really anxious ones in each group. It might not, because it's random. Randomly, all 10 could end up in one group. Right? Not as likely as 5 and 5. 5 and 5 is the most likely outcome when using truly random assignment. There's no guarantee. So when is random assignment more likely to work, more likely to create equivalent groups? Well, when you have more people. Obviously, like if you only had 4 people, right? And 2 really anxious and 2 not so anxious. Okay, is random assignment going to put 1 really anxious in each group? Maybe. It's pretty conceivable to see that those 2 could end up in a group together and the 2 not anxious in a group together. Now, if I had 100 people, right, and 50 of them are really anxious, what are the odds now that all 50 of those anxious are going to randomly be put in the same group? Not so good. Right? So random assignment has a chance to work, has a chance to distribute those nuisance variables and kind of nullify the effects of them. Those effects get washed out because it's affecting both groups equally. The bigger the group you have, and also the fewer the nuisance variables there are. So you got to think about, okay, here's my dependent variable, here's what I'm measuring. I'm measuring proximity. What are all the different things that could affect proximity seeking? Okay, and there may be more or less variables that affect that dependent variable than some other dependent variable. How much in love do you feel with someone? There may be more variables that affect that, or less. You just have to think about it and think about the major ones, the most likely things for the sample you have. What are the ways these people could be different that is going to affect my my dependent variable? And if there aren't a whole lot of them, then you may be in good shape. If there are a bunch of them, you may need a bigger sample to offset the effect of there being more nuisance variables. The other thing you can do, if you're worried about nuisance variables and you're worried about group equivalence, maybe you just can't get a big sample, it might be important to use matched random assignment. Right? So maybe I can only get 10 people to be in my study. This is going to be low power, I'm kind of worried. I really want to make sure I've got equivalent groups, so maybe I'll do matched random assignment. So I measure these people on the important nuisance variables, however many I can afford to match on. So let's say I'll just do 1. I'll just say, okay, I'll measure their existing level of trait anxiety. How typically anxious are you? You know, line them up. And I'll take the 2 most anxious people and I'll match them. They're equally anxious. So I don't want both of you anxious people ending up in the same group. So I've got 2 anxious people and I'm going to randomly assign 1 to the experimental, 1 to control. Not necessarily the more anxious of the 2 to 1, the less anxious to, no, that wouldn't be random. You'd be cheating. So you match them and then randomly assign 1 to 1, 1 to the other. I've gone down to the next 2 most anxious. Now you're a pair, you're matched. Assign to 1, assign to 1, right? Randomly. Okay? And then I'm kind of stacking the deck in my favor in terms of now I'm more confident that they're equivalent, at least in terms of trait anxiety. They may not be equivalent on some other nuisance variable, at least I matched them on that. And you can match on a couple of things if you have a big pool to pull from. But the more variables you try to match on, the more complicated, the more time consuming and expensive it can become. Okay, in terms of interpreting the results. So we've got, we manipulated an independent variable, right? We used random assignment to get equivalent groups, we used terminal control, we measured we manipulated IV, we measured a DV, and we find a difference between 2 groups, right? So what are we testing? Are we testing whether or not there was an effect of the independent variable? Ultimately, that's what we're interested in terms of the math and the statistics. It's not what we're testing, right? Because it's null hypothesis statistical testing. So what we're testing is the null hypothesis, and the null hypothesis is that there's no effect. So what we're really testing is, was there not an effect? And we want to go say, no, there was not an effect, or how many negatives that is, right? We're testing, okay, are these groups equivalent? I think they should be different because I did something different to them, but I want to know, are they the same? And if they're the same, there was not an effect, right? So I'm testing that null hypothesis. The null hypothesis being the mu1 equals mu2. Right? We're talking about parameters. So at the population level, the population from which these people came, you know, the ones that got the drug, and the population from which the people that came that didn't get the drug, so all non-drug exposed people compared to all drug exposed people, are those population means equal on my DV? If so, they're the same population and there's no difference. But the null hypothesis is that, yeah, that they are the same, and that there's no difference. Mu1 minus mu2 would be equal to 0. They come from the same population. You didn't do anything to affect one group differently than the other. So, when you're testing the null hypothesis using NHST, you know, every statistical test you use that uses that logic will generate a p-value. Everybody's familiar with the p, right? What though does that p-value tell you? And this is something that a lot of people, I think, misconstrue. What the p-value tells you is this: it's a conditional probability. So it's not just, oh, it's the probability of this. There's an if statement before that. So the if is, if the null is true, if there was no effect, if the null is true, then p is equal to the probability of finding the difference that you found. So think about this. If the null is true and you find a difference that's, you know, 0 or 0.001, you find a real small difference. So if the null is true, what do you think the p would be? If the null is true, what's the probability of finding a difference of 0.001? Well, it should be pretty high, right? Because if the null is true, then you should find a difference of 0, because that's what the null is, that the difference is 0, that they're the same. So if the null is true, then p is going to be, and you find a small difference, then p will be big. However, if the null is true and you find a difference that's very, very big, there's going to be a low probability associated with that. It's not common to find a huge difference if in fact there isn't a difference. Make sense? So that's why we always want that small p-value. We want that probability to be low, because if this probability is low, if p is low, then the kind of deductive logic, then the null hypothesis therefore has a low probability of being true. Okay? And p is not the probability that the null is true. It's not. P sets the upper limit of the probability that the null is true. But it can't be the probability because it's based on the condition that, well, if the null is true. So the probability that the null is true, you'd have to know the true probability if the null is true, multiply that by p, and then you would know, based on your findings, what's the probability the null is true. And you can't ever know the true probability if the null is true. So all you can say is, well, it's less than the probability of the null is true is less than the p-value that I found. So if they can, trying to keep it simple because I just kind of go in circles. If that probability is low, if the p-value is low, then therefore the null is probably not true. So we make a decision. We make a decision about the null hypothesis based on this probability, and we use a decision rule, right? In the decision rule we say as well, how improbable does it have to be that we found this huge effect to say that, well, the null is probably not true. But we say, well, it has to be, probably has to be lower than some number. What's that number? That number is alpha, right? That's a number you set a priori before the study. It's not something that will be generated by some analysis or spit out by a computer program. You pick it. You decide what alpha is going to be, right? And generally, the default value is, well, I'm going to set alpha at 0.05, right? Such that when the null is true, I'm only going to say that it's not true if the probability of finding what I found is less than 5%. Right? So if your p is less than alpha, you're going to reject the null. Well, it's pretty unlikely the null is true if I found a finding this big, so therefore the null is probably not true. But if your p-value is greater than alpha, instead of 0.05, it's 0.06, oh, didn't quite get under that threshold, the null is probably still not true, but that's too much probability, it's too much risk. The null might be true. I might get that finding when the null is true, so I'm not ready to reject it. Okay? So you make some decision to either reject or not reject the null hypothesis. And your decision can mean a couple different things, right? So if you reject the null hypothesis, right? So the null is saying that they're the same, that they came from the same population. You're saying, no, that's not true. These groups came from different populations. That, yes, in fact, the independent variable did have an effect on the dependent variable. The difference that I found is an indication of a true difference at the population level, right? Because, I mean, if you find a difference in your sample of 0.001, well, that's a true difference in your sample, yeah. But you don't care about your sample. You care about the population. That's what inferential statistics are about. Based on what I see in a sample, what can I say about a population? So you're going to say, yeah, in the population, this variable will have an effect on this other variable. Okay. The alternative is not to accept the alternative hypothesis. It would be much simpler if it were, but it's not. It's you fail to reject the null hypothesis, right? And failing to reject the null doesn't mean you believe it. You don't accept the null when you fail to reject it. You don't say, oh, the null is true. You didn't prove the null is true. You just failed to reject it. Again, because that goes back to that originally. What are we testing? We're testing, okay, was there were these two groups in fact equal? Right? And if you don't find a difference, it doesn't mean you prove they're equal. It means you failed to show they were different. I know that seems crazy, but that's how logic runs. So all you can say is you failed to reject the null. Okay? And when that happens, what you're saying is that the groups probably came from the same population. I can't conclude that they didn't, and that probably the independent variable had no effect on the dependent variable. I can't say that the independent variable did have an effect. Right? I failed to show an effect. Right? And really what happens is, over time, if a bunch of people fail to show an effect, then we think, okay, now we've demonstrated that the independent variable does not have an effect. But one study typically can't say that. So again, you cannot say that you accept the null, only that you failed to reject it. Okay? So either reject or fail to reject the null. You don't make a decision about the alternative. Your decision is about the null. Okay, so, and you can be right or wrong about this, right? Corresponding to your decision is some reality. And in reality, the null is really true, or in reality, the null is really false. We cannot ever know the reality. Right? There's this knowledge that it exists, but we can't know it, so we can't ever know exactly the probability that we were right or wrong. We can estimate the probability based on inferential statistics, but we can't know exactly how likely it is. So in terms of our decision, if we reject the null hypothesis, but the null was true, so we reject it, no, get out of here, you're not true. Oh, but it was true. Crap, wow, we screwed up, we made an error. Right? And in particular, we made a type 1 error. Right? Because when we reject the null, we're saying, oh yeah, they're not equal, they're different. I found an effect, yay. But in fact, the null is true, they weren't different, there's not an effect. Ah, crap, so I said there was an effect when in reality, there wasn't. I've made a type 1 error. Okay. If I reject the null, and in fact the null is false, then yay, I found an effect. Right? So I've made a correct decision, and I'm really happy about it. Right? Because I've said, yeah, these things are different. I manipulated this into variable, and this difference I observed in my group is representative of a difference in the population. My treatment, my independent variable, had an effect. Right? I'm right. That's a good thing. Right? So when you reject the null, you're either going to make an error or you're going to be correct. When you fail to reject the null, same thing. You're either going to make an error or you're going to be correct. But it's a different type of error and it's a different type of correct. So when you fail to reject the null, and in fact the null is true, so I say, oh, I couldn't show a difference, and in fact there is no difference, hey, you're correct. But it's, sad face, because you're not as happy. You wanted to show there's a difference, because typically you don't do a study saying, hey, is there an effect between this and this? I hope not. Right? You're doing a study hoping to show that there is an effect. So you're right, but it's kind of bad news. Right? So I failed to reject null. There's no difference between people that got my therapy and people who didn't get the therapy. And in fact, that's true. Oh, correct. Crap. So when you fail to reject the null, right, you're saying, oh, there's no difference. You could be right, or you could be wrong. And when you're wrong, you're making an error. It's a different type of error. It's a type 2 error, right? So I failed to reject the null. No, it's not. The null is probably true. I didn't reject it. Oh, but actually, it was false. There is an effect. Your treatment worked, but you said it didn't. Oh, crap. So it's a different type of error. And so these are the 4 possibilities based on every test you run. You make a decision one way or the other. Dichotomous is binomial, binary decision, and there's a binary truth resulting in these 4 possible outcomes. And obviously, the one we want most is that bottom right corner. Yay, we're correct. We found an effect. And if we fail to find one, okay, that's kind of a bummer. But at least we're moving science along, because we can say, okay, well, not that. Let's try something else. Right? So we don't keep trying the same thing over and over again. But over time, a bunch of studies say, oh, this treatment doesn't work. Okay, then quit using that treatment. Right? Let's look somewhere else for the answer. But in terms of the errors, which one's worse? What's the cost of an error? And for a long, long time, people were really worried about type 1 errors. And not so worried about type 2. The pendulum has swung back now where people say, well, type 2 errors are important too. If you're saying something didn't have an effect, but it does, and then we're looking elsewhere for the truth, well, the truth's back behind us where we should have found it, but we didn't. We had a type 2 error. Right? So we're spinning over. So the 2 types of errors have different costs associated with them. Type 1 error, you said there's an effect, and there's not. How costly this is depends on what you're looking at. Right? So let's say it's some sort of treatment study, right? And you say, okay, yeah, this therapy works. It's better than doing nothing. Okay, so now, because we have an empirically based profession, people are going to say, okay, I'm going to do this treatment because this study or these couple of studies, if it was replicated, unlikely a type 1 error to be replicated, could happen. But again, that's why we have replication, to eliminate these type 1 errors. Let's say there maybe just one study. One study had type 1 error. Someone said, oh, geez, I didn't take Dr. Fiala's research methods class, so I don't know. I should wait to see a replication before I adopt this. Look what. So they go and they do it. They do this study. They do this therapy. Oh, it's going to be great. And now they're not providing good treatment to their clients, and clients, aren't going to get well. And depending on what you're treating them for, that may be a really big deal, right? If it's, some treatment for anxiety. Okay, yeah, that's kind of bad because they're going to be anxious for longer, and eventually they'll probably try something else. That's not as bad as maybe it's a treatment that's for working with people of high risk for suicide. Ooh, now if you're doing that and it doesn't work, well, now they may kill themselves. That's a high cost. That type 1 error was very expensive. So you think, well, geez, then I don't want to make a type 1 error. Geez, I'll err on the side of making type 2 errors. So again, what's a type 2 error? It's when you said there wasn't an effect, but there was. So this type of error kind of goes, can be just as bad, right? And if you think about it with a treatment, it could be, okay, here's this treatment, and it's for high-risk suicides. It was said it didn't work, so nobody uses it. Oh, but man, so they're using other stuff, and maybe it doesn't work as well. But man, if they'd been using this thing, it works. They would have gotten better. They wouldn't have killed themselves. But they didn't use it because you said it didn't work. That's a problem too. Right? The other thing about type 2 errors, you think about, instead of treatment, if you're looking at kind of harmful effects, is this thing bad for you? Right? So we do a study looking at, does smoking cause cancer? If we have a type 2 error, we say, oh no, we found no effect of exposure to smoke and the carcinogens in cigarettes on health. Smoke up. Okay, that's kind of a bad thing too. So neither type of error is a good thing, and you want to take steps to reduce both types of error whenever possible. So how do you reduce the probability of an error? Well, for type 1 error, the easiest thing you can do is decrease alpha. Right? So well, if I set alpha at 0.05, then if the null is true, the probability has to be 5%. Well, if I want a more stringent alpha, I say, well, I'm going to reject the null less often, because the less often you reject the null, the less likely you are to make a type 1 error. Right? Like if you just did a study, didn't look at the data at all, right? No analyses, and you go, you cover your eyes and you go, I'm going to fail to reject the null hypothesis. You cannot have made a type 1 error. Yay! Yay! I'm going to say it didn't have an effect without even looking at the data. It's impossible now for me to make a type 1 error. Hey, good for you. But you didn't look at the data. You have no idea what happened. Right? So you very well could have made a type 2 error. And decreasing alpha to some extent follows that philosophy. You make it really hard on yourself to reject the null hypothesis. You're more likely not to reject it when alpha gets smaller. Right? You've got to have a really huge effect, a big difference between groups that generates a really small p-value, and that for that small p-value to still be smaller than alpha whenever you decrease it. That's one thing you can do to reduce the likelihood of making a type 1 error. The other thing, which I think is probably more important, eliminate confounds. Make sure that in everything you can do in terms of assignment to groups and experimental control, that there's no difference between your groups other than the independent variable. Because if there's a systematic difference between groups other than the IV, then that other thing could be causing a difference. And so no matter how small you make alpha, you get this unifying, well, there's this huge difference. Wow, really small p. I can't have made a type 1 error. Yeah, you did. I mean, the groups were different, but they weren't different because of your independent variable. They're different because of this confound variable, right? The statistics, the alpha, the p, that can't deal with confounds. You have to deal with that methodologically. Okay, so you make sure your groups, they're different in no way other than the independent variable. That's about it for type 1, other than, just generally running a better experiment. You should be less likely to make an error overall. So a lot of the things we're talking about for type 2 also help with reducing the likelihood of type 1, but these things most directly. Okay, in terms of type 2 errors, you want to increase power, right? Because power is your ability to detect a significant effect. Low power, probably going to make a type 2 error. High power, probably not going to make a type 2 error. They're directly inversely related. Right? So what you can do, well, you can increase alpha, right? And this is the one thing where changing alpha affects type 1 and type 2 directly. right? So decreasing it, type 1 goes down, type 2 goes up. Increasing alpha, type 2 goes down, type 1 goes up. So whenever you monkey with alpha, you're going to be more or less likely to make one of those types of errors. So you find an alpha that's in the middle, right? And given that there's, as we'll see in a bit, a whole lot of other things you can do to increase your power, I'd say don't worry too much about increasing alpha to deal with your type 2 stuff. Leave your alpha at 0.05, even maybe go a little bit lower, 0.01, to deal with type 1, and then do all these other things to increase your power to deal with the probability of making type 2 error. So again, eliminating confounds won't increase type 2 error, and then doing all these other things we're talking about for type 2 won't increase your likelihood of type 1. The only thing that's this kind of clear relationship is that monkeying with alpha. It affects them inversely. Okay, so you can standardize your procedures, right? So instead of telling your experiment, okay, go in and tell that group, they're going to read some stuff and answer some questions, and you kind of know how it goes. Give them an exact script so that you know they're reading exactly this, and then when they do the other group, they will read exactly the same thing, same time, right? You're standardizing it so everything's the same. It's about exerting experimental control, right? When you do that, you're going to be eliminating error, right? And that kind of random error that's distributed across groups equally. Both groups are getting jacked up with this error. It clouds your ability to find an effect and it reduces your power. So the more you standardize your procedures, the more you're cleaning out that error. Choose sensitive and reliable measurements, right? The ability to measure your construct accurately, clearly, reliably, and sensitive to small differences will directly affect your power, your ability to find a difference, right? If you have a really insensitive, unreliable measure, then okay, there may be a difference, but you couldn't find it because you didn't measure it appropriately. Another thing you can do is get homogeneous groups, right? Or really, I should be saying a homogeneous group, homogeneous sample. So again, we want equivalent groups, one in each, but before that, your sample, because we think, oh, I want a good diverse sample that's representative of the population. Yeah, for external validity it's good, but for being able to find an effect, right? One of the things we talked before about was with matched random assignment was, okay, there's all these nuisance variables, we want to reduce their effects by making two groups as similar as possible. One way to make two groups as similar as possible is start off with a group where everybody's pretty similar to each other, right? So not getting a diverse group, getting people that are all from the same community, all about the same age, same cultural background. Now, how the external validity of that's going down the crapper, right? Well, it's just about these exact people. They're different than lots of people. Yeah, that's a problem. But really what you're worried about is, can this thing have an effect? The first of its kind, can this therapy work? You might want to get a homogeneous group. That way you're reducing all these other potential nuisance variables. If these people are already all the same on those nuisance variables, you don't have to worry about getting, the same amount of anxious here and here, because everybody's equally anxious. They're all homogeneous. They're all the same. Okay, so it's got its drawbacks, but good for increasing power. Along those same lines, the other thing that you can do kind of directly mathematically to increase your power is get a large n. The larger the sample, the more power you're going to have to find an effect. Okay. So much so that sometimes when we see really large n's, we wonder about the meaning of some statistically significant findings, because things that are kind of spurious correlations or really minor differences, they'll show up as statistically significant just because we have huge samples, talking about thousands of people. But if you have this kind of effect that's kind of small, well, you're probably going to need a lot of people to tease apart that one thing, because a lot of things are probably affecting the DV. If you want to figure out just this one, I think this one thing is affecting it, means a lot of people big in. The other thing you can do methodologically is use extreme levels of the independent variable, right? So instead of therapy versus no therapy, a whole lot of therapy versus no therapy, right? Or if I'm looking at that, a scary sound versus a not scary sound, right? I don't want it just to be a little bit scary. I want to get the way scariest stimuli as I can, right? And again, how generalizable is that? Maybe not really. But if I just want to show that it can have an effect, showing some scary sound, proximity syncing, then I'm going to use kind of the extreme end of the IV, the most of that construct, whatever that I'm looking at. Because once I find that, we'll do another study and see if it works at smaller levels. But again, that can increase your likelihood of finding an effect to really push the independent variable to its maximum. Okay, so we've talked about the basics of experimental study, which applies to all this stuff, and we've talked about the decision making, which applies to all this stuff. But we did that before talking about multiple groups because it's just simpler. The logic is the same. It's just now instead of saying, oh, control an experimental group, you're going to have a couple of groups. But like the null hypothesis stuff being mu1 equals mu2, it's mu1 equals mu2 equals mu3 equals mu4 if you have 4 groups, that all the groups are equal. Right? But other than that, the logic pretty much stays the same. So, what's different? Well, you're using more than 2 levels of an independent variable. This isn't just about groups of people. This is, when we say group, we're talking about, okay, they're a group because this group all experiences the same level of the independent variable. This other group experiences the same level of the variable as each other, but different than that other group. Right? So again, it's the same logic regarding null hypothesis statistical testing. And right now we're still just looking at 1 DV at a time. Right? And you can do an experiment with multiple DVs, but we're thinking about the stats of it. Okay, do these groups differ on this variable? Okay, do they differ on this variable? Not, do they differ on all these variables at once? It's on down the line. So one independent variable at a time. And still, the only difference between groups is the independent variables. If I have 4 groups, A, B, C, and D, A and D are exactly the same except for the level of the IB they get. A and C, exactly the same except for the level of the IB. C and D, exactly the same except for the level of the IB. Got me? Okay. So, why use more than 2 groups, more than 2 levels? Lots of reasons. One, it can help improve external validity. Right? Most things in the world are not dichotomous. Right? Scary sound, not a scary sound. Generally, the amount, how scary it was, or the degree of scariness matters. Right? It's an interesting question. So I might want to find, okay, when it's just a little bit scary, no proximity seeking. When it's a lot scary, it is not scary at all, no difference. Okay, so I find that, okay, it's at a certain level that this variable has an effect. Right? Related to that, using more than 2 groups, more than 2 levels, allows you to identify potentially the functional relationships between variables, between independent and dependent variables. And one thing you can look at is, okay, is there a clear linear relationship? Right? So the scarier the sound, the more proximity seeking happens. Or maybe there's a curvilinear relationship. So little scary, proximity seeking, scarier, they sit even closer. Then you get real scary, they run away. They don't seek proximity at all. Could be, right? Whereas if I just use 2 groups and I use my scariest one versus not scary at all, they might be running away and go, oh yeah, scary sounds don't cause proximity seeking, they cause distance seeking. Well, that's not necessarily true. It's the super scary sound, but at lower levels, yeah, the scarier it is, the more proximity seeking can happen up into a point. Right? So we identify the function. Think about the graph of that relationship. Is it linear? Is it non-linear? Is there any kind of cut point, if you will? So something that is probably important to think about if you're wanting to establish external validity. So, okay, I'm going to use different levels of scary. Okay, well, how do you know which levels to use? You're going to say, oh, this is going to be twice as scary as that. So you're trying to scale the independent variable. And often you do that with a pilot test, right, where you get several variations of your independent variable. Okay, here's a little bit, here's a sound, here's a sound, here's a sound, and you get people to rate them on how scary they are. Then you use these data to help you choose which stimuli to use. Okay, these on average were rated a 2, these were a 4, these were a 6. I'm going to use those, not the ones that were rated a 3 and a 5 and a 1, whatever, so that you know the relative relationship among those things. Okay, this is a little, this is moderate, this is a lot, versus just guessing. The other thing that using more than two groups, more than two levels can do is improve your construct validity, which we know having better construct validity ultimately adds to both external validity and internal validity. One thing it can help you identify are potential impurities in your manipulations. Because when we try to make two groups differ by manipulating a different variable, sometimes we end up manipulating more than the construct we're calling our IV. Right? So when groups differ in more way than the IV, what's that called? Well, an impurity or a confound, right? Let's say, for example, I want to look at the effect of social media use on studying, right? So maybe I say, okay, people use Facebook or not use Facebook. Well, what if by manipulating Facebook use, I'm assigning them to get on Facebook, what if that involved more than just social media use? Maybe there's something else going on in Facebook that's not common to all social media, right? So then think, okay, well, I'll use another group. So also people use Twitter. Now, if both the Twitter and the Facebook groups, if they're not different than each other, right, in terms of study time, academics, whatever, but they are both different from the group that didn't use social media, then yeah, okay, I manipulated social media use, that's good. But if I find that Facebook and Twitter groups are different from each other, then I've discovered there's something else going on. There's some sort of impurity or confound. And you can identify those things if you use multiple groups. Okay, and the other thing to mention with construct validity is there may be qualitative differences in your IV, right? We're going to talk about kind of quantitative differences. We talk about, you know, the functional relationship, so more or less of the independent variable. But what if it's kind of different types of the thing you're calling the independent variable have an effect, right? So you want to know, you know, what's the effect of putting somebody in public school versus private school? And well, that may be may tell you something. But what if private schools aren't all the same? If public schools aren't all the same, so you may look at more than one kind of private school, right? Or maybe more than one kind of public school. Right? If you do that, you're going to get a better idea of what the construct is that's responsible for the effect that you're finding. Additionally, you can improve internal validity by using more than two groups. And the primary way that it helps with this is in terms of hypothesis guessing, right? Because when you just have two groups, you have experimental and control. Typically, you have one of two choices for your control group: an empty control group where, you know, nothing happens. Okay, so you're going to get therapy, and you're going to sit in a room and not talk to anybody. So you're not getting no therapy, right? Or you're not even going to come into a room, right? We're just going to measure your depression after, you know, you're going to be put in the study. Somebody else is going to put in the study. They get therapy. You don't. 2 weeks later, they're going to come in and fill out a depression measure. You're going to come in and fill out a depression measure. See how depressed you are. Okay. If you're in a study and they're not doing anything to you, there's some demand characteristics associated with that, right? And you think, well, nothing happened to me, so I guess I'm the same, or maybe worse, right? If you're trying to help out the experimental. The other thing is the placebo control group, right, which especially in clinical studies can be problematic because so you're going to get therapy, you're going to get somebody talking to you but not doing therapy. Okay, well, how do you talk to somebody without doing therapy if you're a therapist? It can be tricky. So if you're worried about these possible effects, using multiple groups can help you kind of tease apart, okay, when I'm saying there's a difference between this therapy group and this other group, what does it really mean? So you can use, you know, both types of control groups. Use an empty control group, use a placebo control group, and then use your experimental group. And then really, best practice would be use another experimental group that just gets a different type of therapy. Then, depending on the pattern results, you can be, you know, more or less confident about what's going on. Like if your empty control and your placebo are exactly the same, they're no different than each other, but both are different from your therapy group, okay, now you've got some confidence about what's going on. If those two are different from each other in any way, okay, now you're not so sure maybe what that means and what really happened to your control group other than not getting the independent variable. In terms of the statistical tests you use in experimental research, a lot of different things, but at the most common things you'll see is what we'll talk about here. If you're doing a simple experiment with just two groups, typically it's one of two things: either an independent groups t-test, right, and you use an independent groups t-test whenever your dependent variable is continuous, right? So I'm measuring proximity seeking, so how close do they sit to somebody, and I measure, you know, in centimeters, millimeters, whatever, how close or far they sat. That's a continuous variable. It can occur at more than one level. I'm going to use a t-test. If I used a categorical measure of dependent variable, so if someone said how many people sat closer versus how many people didn't sit closer, so the frequency of something, then I'm looking at a chi-square test, right, a non-parametric test. And typically for two groups in an experiment, that's what you're going to use. There are some other things, but one dependent variable, you know, do these two groups differ on this one dependent variable? It's going to be an independent groups t-test or a chi-square test most of the time. Again, if you have continuous data versus categorical data. If you have other kind of funky data, rankings and stuff, it may be something different, but for most of the things you'll look at, this is what you'll use. Okay, what about if you have a multiple group experiment, so more than two groups, more than two levels of the independent variable? Typically, you start off with some sort of omnibus test, which isn't, I did the omnibus test. Omnibus is just an adjective meaning an overall test, right? And you do that instead of doing multiple pairwise comparisons. And the reason you do that is the more tests you do, the more likely you're going to make at least one type 1 error, right? Because, okay, for this test, I've got some probability to make an error. For this test, I got some probability. For this test, some probability. So overall, what's the probability? Well, more than any one of those individually. Just like when you go out driving, knock on wood, nothing's going to happen to you. You're fine. When you go out driving once, there's some chance you're going to get in a wreck. Twice, some chance. The more you go out and drive, the more overall likely that you're going to get in a wreck at least once, right? It goes up. That's what the family-wise error rate is, or inflation of type 1 error, rate. The more you do something, the more likely it is this thing that could happen for one thing, more likely it's going to happen overall for all those tests is going to happen. So because of that concern, and you don't have to, this is just kind of what's developed in the field as a practice, is you do this omnibus. One big test is, okay, overall, looking at all these groups, so I've got 3, 4, 5 groups, is something different going on among all 5 of them? I can use one test to tell me if there's something going on different among those groups. Right? And that omnibus test, the most often used, again, if you have one dependent variable that's continuous in nature, would be an ANOVA, or an analysis of variance. And what it does, pretty simply mathematically, you get this F ratio, which is simply a ratio of between groups variability to within groups variability. Right? So, because within each group, people are going to differ from each other. Right? And ANOVA has a way of adding up all that variability, and the degree that people differ from each other is called error variance. It's not error in terms of wrong, it's just not related to the independent variable. Right? So there's some amount of error variance in all those groups, and you kind of add all that up. Right? And then each group should differ from each other group. Right? And one group is going to differ from another to some degree because of that error variance, because individuals differ from each other. But some of that difference between groups is going to be associated with why the groups are different. And the groups are different because of the independent variable. So when we look at that ratio between groups to within groups variability, generally, the bigger the ratio gets, the more likely it is that those groups are somehow different. Okay? So, but when you do an ANOVA, and you go, oh yeah, I got a significant F equals 4.78, P equals 0.03, super, great. So groups A, B, C, and D, at least one of those is not like the others. Which one's the biggest? You're not done. Now you have to go through and do the thing that you couldn't do before. You do post hoc tests, and you're doing those pairwise comparisons. So you're still doing pairwise, you're still doing multiple tests, right? But now you're saying, okay, well, I've jumped this hurdle, this probability hurdle, that allows me to do these tests. So I don't think I'm going to make a type 1 error because I know there's an effect there. Right? Because if your ANOVA is not significant, you can't do the post hoc test. You can say, well, the ANOVA is not significant. We still look to see which group's different. No, can't do it. Well, shouldn't do it. So now you kind of allowed to do these pairwise comparisons. Okay, which groups differ significantly from each other? And it won't always be all of them. Sometimes it'll be, well, one group different from all the three others, but they didn't differ from each other. Or, A was bigger than B, and A and B were both bigger than C and D. There's all kinds of patterns that can occur, and you got to tease that apart with your pairwise comparisons that are done post hoc, after the fact. So after the ANOVA is really what it is. And again, as we said before, all these tests that we're talking about generate a p-value, and you know what it means now. And the p-value is important. Right? It tells you to compare it to alpha to determine if you have a statistically significant difference, which you could then logically infer that difference implies a statistically significant effect. Okay, and that's important. But in recent years, past 20 years now, there's been a recognition that that's nice. That's not everything. So now there's this more recent emphasis on effect size. Okay, so it's a statistically significant effect. How big of an effect was it? A little bitty effect that was statistically significant, or was it pretty big? And you think, well, the difference in groups was, was 4 points, or it was 6 points. So that was 4 big or 6 big? Well, it depends on what measures you're using. And what effect sizes do is they take whatever differences you have and they standardize it, just like the standard deviation does. We say, okay, these groups have this much variability, this much variability. What's the standard deviation? Right? And you can compare standard deviation of one group to another using different measures, and you can still compare. Okay, one has more variability than the other because it's a standard deviation. And effect sizes are these kind of standardized effect sizes where, okay, an effect size of 0.2 using this measure is bigger than an effect size of 0.1 using a completely different measure. It's still bigger because it's been standardized along this, using these statistical procedures. Right? And there's a couple different ones: Cohen's d, r squared, eta. But those are the things that you're being called on more and more to report, and the things that you should be looking for when reading articles. Did they report the effect size? And how do they interpret the effect size? Is that small, moderate, large? And also, most importantly, I'd say is, whenever they say it's large in effect size, based on what? Because if it's small, medium, or large, depends on what field of study you're looking at, right? Because usually it's small, medium, or large compared to effect sizes other people have found with that dependent variable or with that independent variable. Okay, after you've done your statistical tests, you've made your decision to reject the null or fail to reject the null. Maybe you got some questions about what it all means. Well, again, you have two potential outcomes with your null hypothesis. Null hypothesis statistical testing. Non-significant results, oh no, my p-value was too big. Or significant results. If you get non-significant results, why did it happen? Right? You got to think about that. Well, was my n too small? Right? So maybe it was underpowered. So again, this going back to thinking about, well, how do I reduce the likelihood of type 2 error? I get a bigger n. So was my n too small? And really, what you should have done, if you didn't, before you do the study, you do a power analysis to see, well, how big of an n do I need to detect an effect size of what I think I'll encounter? So do a priori power analyses rather than after the fact. But if you knew it before, at least in your own living room, you can say, geez, was my n big enough? You don't write that in your paper. You don't do a power analysis after the fact. But you could cite it as a limitation. If I failed to find an effect, but it could be because we only had 10 people that showed up for the study. When we tried to recruit 1,000, 10 completed their measures. The other thing about is diversity of the sample. Right? So maybe it was too diverse. Because remember, easier to find an effect if you have a homogeneous sample. So if there's all kinds of different people there, maybe that's why you didn't find an effect. So maybe your variable really does have an effect, but you couldn't see it because there's so much going on. Maybe you screwed something up. Right? Maybe you had messy design, or execution. You designed a really good study, but then you hired these grad students or whatever to run it for you, and they were sloppy and had introduced too much error variance, maybe even confound. Right? So there's something going on there that led to the failure to find an effect. Was maybe your measure of the dependent variable not reliable or sensitive enough? These are all things we talked about before. And lastly, maybe was the manipulation of the variable just not strong enough? Okay, so I didn't find. So again, and you're asking yourself these things if you believe in kind of the theory that you were testing, and I really think this has an effect. Why didn't I find it? Maybe it's this, maybe this, maybe this. So when you do your next study, you address whatever the most likely culprit was. Right? You use a stronger manipulation of IV. You get a more homogeneous sample. You get a bigger N. Whatever you got to do, whatever you think caused the problem, you address it in the next study. Well, if you get significant results, you celebrate, right? Yay! Yeah, but if you're a good scientist, you also go, okay, I found what I thought I was going to find, and that's good. I'm proud. I'm happy. But let's think about it for a minute. Were there any confounds? Am I sure? How confident am I that this difference that I found, which is statistically significant, yay, that it's because of the IV and not because of something else? So when I manipulated this IV, did I introduce any impurities? Was there something that happened when we executed the study? If not, okay, feel good, sleep better. If not, okay, now you got to report, well, this difference may be due to blah, blah, blah. This thing I thought of after the fact. Whoops, my bad. The other thing, effect size and clinical significance, just like we just talked about. Okay, I found this statistically significant effect. What's the effect size? Compared to other studies in this field looking at these variables, is it about, is it bigger, is it smaller? Did I find a bigger difference than other people have found using, so I'm treating anxiety. These other studies, they found, their treatment worked, and they had an effect size of 0.2. Hey, my study worked, I had an effect size of 0.4. Okay, twice as big an effect size, that's a good thing. I'm going to comment on that. Versus smaller effect size, I may comment on that a little more quietly. But you still got to say it. Because again, you may get a statistically significant effect that has no clinical significance. Okay, yeah, there was a difference between the two groups, and it's statistically significant, but using this treatment versus using nothing, they only got slightly less depressed. So much, there's such a small difference that it's not really worth it to make people go through, these 20 weeks of therapy if it's only going to move their depression this much. It's not a clinically significant difference. And how big a difference is it to be clinically significant? It depends on what you're talking about. It depends on the clinician, right? That's a fairly subjective thing. There is no math to tell you what yields clinical significance. And finally, you want to think about generalizability. Once you're kind of comfortable with internal validity, okay, I thought about this, the confounds, this, that, I'm good. Okay, this had an effect, it's important, it's big. Now I think, okay, how generalizable is it? How far from the type of people I had, my sample, can I generalize this effect? How far from the experiences they had, all the experimental control I exerted, this manualized treatment, whatever, how far from that do I think I can go when saying, oh yeah, I think this therapy is going to work? Right? And again, that comes down to you thinking about it. There's no math for that part. Okay. So that's the introduction to experimental research, and I hope that made sense, because it gets more complicated from here. That's all for now. Take care.